Welcome back. In this video, we'll be looking at some variants of linear regression. We are still in week 3. Recall that so far we had seen simple linear model, which was y hat equal to w0 plus w1x. We had also seen the quadratic model, which was y hat equal to w0 plus w1x plus w2x square. All these were models where we just had one single feature, which was x. Then we saw that we could extend our analysis to polynomial models, and I showed a few examples of this in the last coding video. So w0 plus w1x, w2x square. You can add a cube term and go on till w1 x power n. Now, all these simply can be abstracted into a single idea of a linear model, the generalized linear model. And the same generalized linear model can also be used for what is known as multiple regression or multilinear regression. So in this case, y hat equal to w0 plus w1 x1 plus w2 x2, where x1, x2 are different features. And you can keep on going till wn xn. So for example, if x itself is made up of multiple parts, x is a vector, x1 through xn. Okay. So you can use this multiple regression. Now we can also see that there is a one-to-one correspondence here. That is, you can think of x as simply x power 1 and x2 as x square, and this is how we actually solved the linear model. And all of these, including this, can be handled with normal equations, which we saw in the last couple of parts. Now, what we are going to do in this video is to look at variants. Now, this is already extremely useful, as you would have seen. This is already very useful, and it encompasses a large number of models. But we can extend this further, and there are several variants of linear regression that exist in various forms, and we are going to look at that in this video. Okay. So we have been consistently minimizing the following objective, residual, or loss function, which is summation of y minus y hat I square. If you go back to the very first video where we did this in week 1 or week 2, I believe, I think it is week 2, you saw that the original form was something slightly different. We had this scaled by yi minus y hat I square by sigma square. Okay, and we'll come back to this point, but generally this is what we have been looking at. Okay, so this is what we call least square regression, or LSR, or sometimes it's called ordinary least square. Okay, you'll see all these names within the literature. But we have other variants. Okay, so we have other variants. Each of them have their own uses. So for example, we can change J itself. Okay, so one change is, so notice this is called an L2 loss, because this power here is 2. We can also do this, okay, which is just summation of yi minus y hat I. Now, why should we add squares? We can also add absolute values. This, of course, is not differentiable. So that is, we can minimize the sum of the individual losses, and we will see what kind of utilization it has. If time permits, we can try to see this within the machine learning setting within the last few weeks of this course. If we have the opportunity, I'll come back to that. Another choice is what's known as the L infinity. Notice this term, L infinity. All this depends on a quantity or variations of what I call norm the last time. So you can look at L infinity loss, also called the minimax loss. So that is minimizing the maximum difference. So what you do is, instead of just minimizing some of the gaps, you see which one is the maximum different thing between your model and your prediction, and you try to minimize that. This of course works poorly in case you have outliers. But again, if time permits, we will see some uses of this towards the end of this course. Okay. The final one is the example that I showed here. It is called the weighted least square. So you can notice that if I set lambda I equal to 1 over sigma I square, you have a slightly different version. You don't have just the sum of least squares, but each of the squares is weighted by a different quantity, lambda I. So this is what leads to what is known as the weighted least squares approach, and we will see that within this video. We will not be seeing these two, but this we will see within today's video. Okay. Now, apart from this, there are also a couple of other variants that can be created, or problems which can actually come from other functions. So seemingly nonlinear functions can be mapped to linear functions. Now, a simple example of that is here. So for example, we had x square, and we simply call this x1 and x2, and now what looked like a nonlinear function looks like a linear function. But of course, this was still linear in W0, W1, W2. But let us say we have a nonlinear function in the parameters itself. So the parameters we want to determine, suppose it's nonlinear there, it can be turned into a linear form through transformations. Okay, so let me give you a trivial example, and then we'll see more important examples that directly arise, especially in heat transfer. So suppose somebody has a model saying y hat equal to W0 square plus W1 square times x. Then you will say, okay, I'll just call W0 square as let's say C1 and W1 square as C2, and now it is linearized. So this is a simple example of how a seemingly non-linear function can be turned into a linear function, but this is of course a trivial example. I'm just renaming constants. You can do something a little bit more clever, and again, you would have kind of done this probably at school too, but we'll just see the context here. Okay. The important thing is that it should be linear in the parameters, okay, and not necessarily in the functional form. So here is an example. Y equal to ax power b. Okay, so suppose we take this example. Y equal to ax power b. So now notice it is kind of linear in A, but this multiplies some x power b, so it looks non-linear. However, if we transform this and take a logarithm on both sides, and we have ln y becomes ln a plus b times ln x. Okay. Now we do the renaming. We call this variable as y hat. Y hat is now ln of the previous y hat. This I call w0. This I call w1. And this can simply be a feature, or you can call it some other variable z. So now you have y hat equal to w0 plus w1z, and this is once again a linear problem. Okay. So this is a simple example of a linear problem. Let's take this one, which can subject itself to the same kind of trick. Okay. So this kind of example, if you remember from the first week, this kind of occurs within an infinite fin. So there you would have something like theta equal to theta b e to the power minus mx. So the parameters of the problem are these two, theta b and m. These are the unknown parameters that we will typically solve in an inverse problem. So if we take this example, or let me take this example, theta equal to theta b minus mx, then I can take ln theta is ln theta b minus m times x. So now this we can call y hat, this we can call w0, this we can call w1, and this is of course x. So we once again have the form y hat equal to w0 plus w1x, which is linear. So just through a transformation by taking a logarithm on each side, we got there. Here is a very popular form. This is, of course, again coming from heat transfer. This is, you will have, in case you remember from heat transfer, this convection relationships, or if you have multiple correlations, they come in the form of what is known as the Dittus-Boelter equation for a pipe. Okay, so stuff like that. When you come here, once again, you now have noticed this case of two features. Okay, so now this is not just x, this is x1 and x2, and your output is y. So if we take that case and we do a Nusselt number equal to some constant re power m, Prandtl number power n, and we wish to determine what m and n are using a lot of data points. Again, we take a logarithm. Logarithm of Nusselt number is logarithm of c plus m times logarithm of Reynolds number plus n times logarithm of Prandtl number. This we can call x1. This we can call x2. This is w1. This is w2. This is w0. This is y hat. And just renaming these variables gives you y hat equal to w0 plus w1 x1 plus w2 x2. So this kind of tricks you can do multiple times. I'll show you one further example. You can come here. So if you come to this expression here, this doesn't look like it is a simple linearizable example. However, with a transformation, once again, of setting one variable as 1 by x and another variable as 1 over y. Let me show you that trick here. So we had this case of y equal to ax plus b plus x. So now take 1 over this. So 1 over y is b plus x by ax. This gives you 1 over y is b by ax plus 1 over a. Now once again, you call this as y hat. Take this b over a, call that as w0. Take this 1 over x and call this as x1. Instead of calling this w0, I will call this w1. And 1 over a, you call w0. And once again, you get y hat equal to w0 plus w1 x1. So this is once again linear. So all sorts of cases that you can work out. Now, unfortunately, you take some cases like this one. This, regardless of what trick you try, will always be not linearizable. So there is no simple rule that I can give you to tell which one will be linearizable and which one will be not. But in this case, it happens to be not linearizable. Any trick you do will not turn it into a linear problem. Okay, so you have a here and you have e power minus b here, and this is always going to be non-linear. So for this is what we will do next week. We have what are known as non-linear regression analysis. Okay, so we will do non-linear regression analysis here. Now, another case where this is of great use is in cases like y equal to a e to the power minus bt. This can be linearized because, as you can see, it's exactly of this form. Y equal to a into e to the power bx. Now, this example we will use within the exercises today, this week, for unsteady conduction. So the exercises for week 3 will have an unsteady conduction example, which you are supposed to convert to a linear problem and then perform linear regression. Okay, so that is the exercise for this week. So what we saw now in the first part of this video is that there are multiple equations or multiple forward models which can, even though they look non-linear in the parameters, can be turned to be linear in the parameters simply through a transformation. Now we are going to look at this all-important case of weighted least square. Okay, so now I want to show you this case of weighted least squares. Remember what I had said, that typically our loss function is sigma of yi minus y hat I square. This is, of course, the model. This is reality. So all we are doing is we are weighting each of the data points the same. That is, the error in the first point is the same as has equal importance as the error in the second point. Now imagine you have a few friends and one person says something like, this movie is good. And even though their taste differs from yours, you know that they are at least reliable. Whereas one other person keeps on like varying their outputs. Okay, so they are very, very unreliable. Another way to say it, so you are not going to weight the information by the first friend the same as the information by the second friend. Similarly, if you have multiple sensors in a slab, let's say multiple thermocouples, and each of them, like some of them are old, some of them are new, and each of them is giving a reading, you cannot weight them. Okay, so these have different accuracies. You cannot give equal weightage to all of them. Okay, so this kind of experiment which I am showing here is one such example. It's one of the oldest examples of a data set. You can see this from 1877. This is by a botanist, whatever language we wish to use. People then were multiple things: statisticians, botanists, etc., etc. So this is by a person called Galton. And the idea was this: he was measuring peace. Okay, so mutter, as they say in Hindi. So he was measuring peace, and he was trying to see how the parent P diameter affects the child P diameter. So progeny here means child. So here is the diameter, and this is not one single parent. Obviously, he's measuring up to 10 children from a given parent, etc. And all these are statistical. There are a lot of data points. This kind of is the mean or an average of this data point. So what he saw, of course, was that there is some kind of correlation. So you can see that as parent size decreases, as it is with human parents, the child size also decreases. But notice that all these things are different. What are these? This is the standard deviation. All of you would be familiar with standard deviation from school. So remember, you would calculate sigma equal to square root of y minus y bar square divided by n minus 1. We'll come to this definition again when we come to the statistics portions. All you need to know is that not all data are equally reliable. Of course, in this case, the variation is small. For example, this varies a little bit less at this size compared to something like this. Okay, so this was, if this is 16, then this is 20. So 0.016, this is 0.020. But nonetheless, these are at least different variations. So the question is this: if you fit and you want to account for the fact that the errors are different, do we actually make a difference in the fit? Will the coefficients actually change? Once again, we are going to try a linear model. This is x now, this is y. So we are going to say y hat equal to w0 plus w1x. But we want to see whether w0 and w1 will depend on whether the accuracy of the sensors is more or not. In this case, the accuracy of the measured data is more or less. Okay. So the way this makes a difference, of course, is the difference that I had shown you earlier, which was to say that J is no longer simply yi minus y height I square, but I want to scale this by the inverse of the standard deviation or inverse of the variance. Sigma I square is called the variance, as you might remember. Sigma I itself is the standard deviation. So we can write this as sigma of lambda I yi minus y hat I square. I don't want to use w because many people use w here, but w we have already used for the parameter. So lambda I are the weights, which is to say, if it is highly accurate, then sigma will be 0. Then I want to give a lot of weight to it, because now lambda is going to be 1 by sigma I square. We will see a probabilistic kind of derivation to this idea when we come to the probability portions of this course. Okay. Now, how does this make a difference? So remember, now I'm going to write J equal to sigma of lambda I yi minus y hat I square. Okay. Now, I have to set the same thing. Del J, if I have a model with W0 and W1, I have to set del J del W not equal to 0 and del J del W1 equal to 0. And this would say del J del Y hat into del Y hat del W not equal to 0 is the first equation. So if you notice this will basically give me sigma of lambda I y hat I minus yi equal to 0. Why? Because del J del Y hat is now going to be lambda I times y hat I minus yi. Almost no change from before, except this lambda I is extra. Similarly, if I do del J del W1 equal to 0, this will give me del J del Y hat into del Y hat del W1 equal to 0. So this will give me sigma of lambda I y hat I minus yi multiplied by xi equal to 0. So these are two equations. And of course, y hat I is W0 plus W1 xi. So if you write these equations out, I'm going to skip some steps. I would request you to go back to your notes for the case without the lambdas and check with this. But if you open this up, let me just open this up just for one case. Lambda I W0 plus W1 xi minus yi equal to 0. So the first equation is going to become sigma lambda I W0 plus W1 into sigma lambda I xi, that comes from here. And this term moves to the right hand side and you will get equal to sigma lambda I yi. So if I write this in matrix form, just like last time, I have W0, W1. So you will see that the first term is multiplied by sigma lambda I. The second term by sigma lambda I xi. And on the right hand side will be sigma lambda I yi. You go back to your notes and check. You can check the normal equation mode also. This would be sigma 1, this would be sigma xi, and this would be sigma yi. That's what happens when all of them are equally weighted. So really speaking, all we have is the same set of equations, except in every sigma, there is an extra lambda sitting, which is not surprising. Okay, so if you go back to your notes, you will see that all you will notice is instead of these lambdas, if you just replace this lambda by 1, you will get the previous one. And if you replace each of the sigmas with wherever there is a sigma, you put sigma of that multiplied by lambda I, you will recover the weighted least square equations. Okay, so these are the and you just need to solve these for the values of W0 and W1. Obviously, this is affected by the value of lambda. Now, if the variation in lambda is not much, you can kind of take out sigma lambda out more or less as an average in lambda. In this case, the variation is not much. So you cannot expect too much of a big variation in the predictions of W0 and W1. If the variation in lambda is high, then you can expect, of course, a big variation in W0 and W1. So I'm just going to quickly show you a code for this, and you are welcome to write this code using the normal equation approach. I'll quickly derive the normal equation approach again without too much detail, but you can use that for there is a weighted least square example given in your assignment 2. You can use some version of that by yourself. I'll encourage you to write a code by yourself for this. So what I am showing here is a code for the Galton data, and I have written coding the inverse conduction problem, which is I should change it to the weighted least squares problem. This is a copy paste issue, but so let's come here. The forward model is still W0 plus W1x. Notice that I have done the same trick. I have cut and pasted whatever I had in my slide here. It's just a convenient way of doing it. I encourage all of you to do this within MATLAB scripts. Now, the thing that has changed, of course, is that the weighted least square formula is now lambda I times yi minus y hat I square, where lambda I is 1 over sigma I square. Sigma I are the standard deviations given in the data set. Okay. I have now written this data out. You can see that here 0.21, 0.2, 0.19, etc. And as usual, I have taken a transpose. I have also written the y data, just like before. You can compare this code with the inverse conduction code also. The extra thing here is the standard deviations, which basically measure how accurate or how much confidence we have in each one of these data points. So the first one represents our confidence in the 0.21, 0.1726 data points. The higher the confidence, the higher the weight you wish to give. Another way of saying is lower the sigma, lower the error expectation, the higher the weight you want to give. So here I have this lambda, so which I have defined as 1 over sigma square. Now, a quick trick I can do just to set the baseline is to declare one sigma 0. The sigma 0 is all ones, as you can see. And why am I doing this? This is to get the ordinary non-weighted least squares. So I can try to get the normal weight square least squares answer without accounting for this. And I will take sigma 0 here just to set a baseline. And the formula remains the same as I had shown you last time. So you have sigma lambda, you can look up your notes, sigma lambda x, sigma lambda x square, and then sigma lambda y, sigma lambda xy. If you remember, the LHS was, which is shown here, sigma lambda x. It was a symmetric matrix sigma lambda x square. On the right hand side, we had sigma lambda y and sigma lambda xy. And as usual, W is equal to LHS by RHS, or inverse of LHS by RHS. So I'm going to run this code just so that you can see the W's. So notice the W at this point, W came out to 0.127 and 0.21. Okay, so this is what happened without, please remember, without the a correction due to least square. So please observe the physical plot here. I have not drawn a parity plot in this case. So the model prediction is the red line and the actual P data are on the dotted lines here. Now, of course, what we need is not sigma naught, but we need sigma. Okay. So this is the actual case. Now, when you run the actual case, you'll see that the value changed. Not by much because there was not huge variation here. Now, suppose I was super confident in some data point. I'll just show you that case. So here you see it has changed by a little bit, but it's hardly visual. Suppose I am really, really confident about this point here and I make this really small. Okay, so now notice how it is doing here versus when I make this really small, it will try to match that a little bit more closely. That is this point. Okay, so this is flipped. So the 0.21. So once again, let me show the difference. If I have 0.019, the gap is high. Whereas if I'm really confident about it and this error becomes really low, 10 times low, it will try to weight the least square line so that it tries to predict that correctly. So this is the advantage of a weighted least squares approach. If we are relatively confident about some points versus others, we can actually weight them appropriately. We'll come back to this when we consider also physics-informed neural networks towards the end of the course. So this here was a simple demonstration of a weighted least square code. This is, of course, explicitly programmed. I'll encourage you to program this in the normal equations approach also. I'll quickly write down the expression for the normal weighted least squares approach shortly. So just to summarize, what we saw was that without weighting, okay, so that is what is known as the ordinary least squares, we saw that the numbers were something like W naught equal to 0.127 and W1 was something like 0.21. Whereas with weighting, which is the weighted least squares approach, we get something like W naught equal to 0.128 and W1 equal to 0.205 or somewhere there. So small change, like I said, the weight change can be large in case the differences in standard deviation are large. Now, the question that we wish to ask is, can we write the normal equations for this? I'm just going to give you the final result. And I'll let you derive it. And if maybe time permits, I'll do it towards the end of the course if required. Otherwise, I'm just going to give you the final equations for this. So define x the same way. You know, x1, x2, etc., etc. The same design matrix, y, etc., also the same as before. But define one extra matrix, which I'm going to call capital lambda, which is a diagonal matrix. This has lambda 1, lambda 2 up until lambda m on the diagonals, and it is 0 everywhere else. Okay, so lambda is a diagonal matrix with lambdas on the diagonal. In this case, the normal equation turn out to be the following. Okay, so they turn out to be x transpose. Remember what the previous equation was? It was simply x transpose xw. In this case, it's X transpose lambda X W equal to X transpose lambda Y. Okay. So, of course, in the non-weighted case, this is the most general weighted least square formula. The non-weighted case was X transpose X W equal to X transpose Y. This is for ordinary least square. You can derive from here to here by simply setting lambda equal to the identity matrix, which simply means that all sensors are equally weighted. Okay. So this is the expression for normal equations. I encourage you to try to derive it in the same way that I derived it earlier. It is possible, but I didn't want to spend too much time on this thing here, where we have other portions to move out to. So what we saw within this video were variants of linear regression. We saw that some of them could be linearized, some functions could be linearized, and some functions deserve a weighted least square approach. Both these are actually sitting within the assignment for this week. So I hope you try the assignments, and I will give you further insight into these procedures. Thank you.